Okay, um, we will end the chapter 1, which covers introductory concepts, by discussing interface between two phases. Okay, so first we will talk about interface between a solid and a fluid. Okay, so consider a solid surface, okay, of an arbitrary shape, closed one, that is kept in a fluid flow. Okay, so the fluid is flowing over this solid surface. Okay, so this is the solid. Okay, so if we consider this particular point, okay, it is within the solid, and if we consider, let's say, this point, this is completely within the fluid. Okay, but on the surface of the solid, okay, so if we consider this surface of the solid, the fluid comes in contact with the solid surface. Okay, so this is the interface between a solid and fluid. So on this interface, on the solid surface, the fluid sticks to the solid. Okay, the fluid sticks to the solid, okay, at the interface. So when the solid moves, the fluid in contact with the solid moves with the same velocity. Okay, because the fluid sticks to the solid, when the solid moves at a particular velocity, the fluid also moves with the same velocity. So what we are trying to say is that the velocity of the fluid is same as the velocity of the solid at the interface. Okay, so this is called, this condition of the equal velocity is we call as no slip condition. Okay, so the fluid does not slip over the solid, rather it moves with the same velocity as the solid. Okay, we will discuss this no slip condition at a later point of this course, and we will develop something called as boundary layer theory. Okay, so this is the interface between solid and fluid. We have only this much to say. Okay, but if we consider interface between a liquid and a gas, so interface between a liquid and a gas, there are some interesting phenomena occur. Okay, if we take a bottle or some vessel and fill it with the fluid. Okay, so this fluid is filled in this container. Okay, so whenever a liquid is that's wrong. So this is liquid, it comes in contact with the gas above. Okay, so whenever a liquid comes in contact with the gas, an interface develops between these two phases. Okay, so this is the interface that develops between these two phases. So this interface behaves like a stretched membrane. Okay, so this interface behaves like a stretched membrane. Okay, this is due to the property known as surface tension. It is due to the property known as surface tension, usually denoted with sigma. Okay, which is given as a force per unit length. Sigma is measured as force per unit length. Okay, so the phenomenon of surface tension arises due to the unbalanced cohesive forces. Okay, so we will provide some explanation for this now. So let us consider a molecule in the interior of the fluid. Okay, so we consider a molecule in the interior of the liquid, and this is surrounded by neighboring molecule in each directions. Okay, hence the cohesive forces act equally in all directions. Okay, so if we consider an interior molecule, okay, forces are in balance. The cohesive forces are in balance. So this interior molecule do not experience any net force acting on it, because the cohesive forces act equally in all directions, so the net effect cancels each other. Okay. However, if we consider a molecule at the interface, okay, so if we consider a molecule at the interface, what happens? Okay, so there is a net imbalance in the force, because we have cohesive forces acting only in the downward direction, because at the top there is no liquid molecule available to exert a cohesive force, right? So to be exactly correct, there will be some adhesive forces between liquid and gas, but this magnitude is much smaller than the cohesive force. Okay, so there is a net imbalance of the cohesive forces. Okay, so the physical consequence of this this imbalance is the apparent tension at the interface, and this is quantified by the unbalanced force per unit length. Okay, so on the liquid gas interface, there is a net imbalance of the cohesive forces. Imbalance of the cohesive forces, and this is what manifests as surface tension. Okay, so the interface behaves like a stretched membrane. Okay, something like a trampoline. You know what is a trampoline, right? If you don't know, just Google it. So the liquid gas interface behaves like a trampoline, a stretched membrane. Okay, I hope the spelling is correct. Sorry about that. Okay, but there is one more important point. Do you see that there is something more that we need to discuss here? It is not just the interior molecule and molecule at the interface. There is something else. Can you guess what it is? No? So we are talking about this point. Okay, why is that point in 2D, let's say this point and this point are so special? Why is it so? Any idea? Okay, so those points are called contact lines. Okay, and actually if you take a cylindrical vessel, it is going to be a line. Okay, so when we say contact line, when we say contact line, a line at which solid, liquid and gaseous phases meet. Okay, so this point initially, what we consider initially, is completely within the solid, and the next point we consider is this one, which is at the fluid gas interface. But these 2 points, okay, in 3D, if you take a cylindrical vessel, it is a line on which all 3 solid, liquid and gaseous phases meet each other, and those lines are called contact lines. Okay, so at the contact line, the cohesive force, okay, the cohesive force within a fluid and the adhesion between solid and the liquid are in competition. Okay, so at the contact line, the cohesion within liquid, okay, and the adhesive forces between liquid and solid are in competition. Okay, so when adhesive forces are larger than cohesive forces, what would happen? Any idea? If you take a small tube, okay, and then you fill this with the liquid, if adhesive forces are larger than cohesive forces, we will get concave meniscus. Okay, this is case 1. Okay, in the other case, when the adhesion is smaller than cohesion, we get convex meniscus. Okay, this is case 2, which is given by adhesive forces are smaller than cohesive forces, so we get convex meniscus. Okay, is that clear? Do you see where physically the surface tension is coming from? That is coming from the cohesive force imbalance at the interface. Okay, and then contact line is the point or along the line in which all three faces meet, and that decides if you fill a solid tube with a liquid, that decides the shape of the meniscus. Okay, and then we will stop this chapter by discussing capillarity, which you already know. Okay, what do we mean by capillarity? Okay, so let us say we have a fluid filled in a channel like this. So we have, we are filling, this is the fluid part. Okay, and then you insert a very small, a tube of very small diameter vertically. Okay, so that is the tube of very small diameter is inserted into the fluid. What would happen? Okay, so the fluid will either rise, or by capillarity we mean the rise or depression of a liquid when a tube of very small diameter is inserted vertically or inclined in a fluid. Okay, so what would happen is that the fluid will rise to a distance h. Okay, and then we have the surface tension forces acting on it. Okay, let us say this angle is theta. Okay, for force balance, the surface tension force is equal to the weight supported in the tube. Okay, so surface tension force is given, surface tension is given by sigma, which is force per unit length. So the vertical force is pi, let us say this diameter is d, so pi d cos theta. Okay, So we are talking about force balance in vertical direction. That is the net vertical force due to the surface tension. The weight supported would be rho is density, pi d square by 4 times h is the volume. So density times the volume will give you mass, times g will give you the weight. Okay, from here we can write h to be 4 sigma cosine theta by rho g t. Okay, so that is a formula for the capillary rise. Okay, so when the diameter of the tube is getting smaller and smaller, the capillary rise height will increase. Okay, this is as expected. Okay, thanks. We will stop here. This ends chapter 1. We will start discussing about fluid statics, which is the next chapter from next lecture. Thank you.